If I asked you to picture the universe, you'd be wrong. Not because you're unintelligent, but because your brain was never built to handle numbers like these. This is where our intuition fails, and space stops making sense until you measure it correctly. So we're going to do something most videos never do. Start small and refuse to cheat. We'll build a scale ladder, one step at a time. Earth, the moon, the solar system, and beyond, until the true scale of the universe finally becomes clear. By the end of this video, you won't just know why our sense of scale fails, you'll see what the universe's size actually looks like when it's built correctly. Before we begin, thank you for being here. If you feel connected to this space, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. We like to believe we understand distance. We look up at the night sky and our brain whispers a simple story. Those lights are up there, the moon is near, the stars are far, the universe is a giant dome, sprinkled with points. But then, we try to say it out loud. The moon is about 384,000 kilometers away, about 239,000 miles. Light moves at about 300,000 kilometers per second, about 186,000 miles per second. And suddenly, the words stop meaning what they used to mean. Because here is the disturbing truth. Our intuition does not fail loudly, it fails silently. It gives us confidence, while it collapses underneath us. And that is where the real mystery begins. Because the universe is not only vast, it is vast in a way that our nervous system was never built to feel. And once we understand that, we see why almost everyone carries the same space illusions, even smart people, even people who love science. But then, if our instincts can't handle the scale of reality, how did we ever measure it at all? We have to start with something uncomfortable. Our senses evolved for survival, not for cosmic truth. Our eyes were tuned for faces, not galaxies. Our depth perception was tuned for trees and cliffs, not light years. Our sense of distance was tuned for a few steps, a few streets, a few hills. Because that's what kept our ancestors alive. We were built for meters and kilometers, for feet and miles, not for the space between stars, not for the scale where near can mean millions of kilometers, and far can mean billions of light years. So when we try to imagine cosmic distances, our brain does something it always does when reality is too large. It compresses, it simplifies, it cheats. And that cheating feels natural. That's why so many space posters show planets lined up like marbles. That's why illustrations put spacecraft near Saturn with Jupiter floating conveniently behind it. That's why, in our minds, we picture the solar system like a neat family photo. Except, that picture is wrong. Not a little wrong. It is wrong in the way a whisper is wrong about a hurricane. And the cost of that misunderstanding is bigger than we think. Because once we misjudge scale, we misjudge everything that depends on it. Time, energy, travel, danger, isolation, even what it means to be close to anything at all. Here is the problem. Large numbers don't feel large. They feel like fog. 1,000 is real to us. We've seen 1,000 people in a stadium. We've walked 1,000 steps. 1,000,000 already starts to blur. 1,000,000,000 becomes a word we say without touching. And the universe lives in those numbers. So our brain tries to protect itself by flattening them into something manageable. And that's where misconceptions are born. We hear the nearest star is a little over 4 light years away, and our mind says, okay, 4, that sounds small, but 4 is a trap. A light year is not a time in this context. It's a distance, how far light travels in 1 year. And light is the fastest thing we know, so 4 light years isn't small. It is the kind of distance that shatters the meaning of near. This is why interstellar travel feels possible in movies. Our intuition silently edits out the emptiness. This is why people assume the asteroid belt is a dense minefield. Our intuition imagines rocks packed like a demolition zone. This is why the moon looks like it's just above the clouds. Our intuition sees it as part of our sky, not part of the vastness beyond our sky. And it gets stranger, because there's a difference between imagining distance and measuring distance. When we imagine, we build pictures. When we measure, we build truth. And the universe does not care what pictures we find comforting. Imagine this. You're standing at the front door of your home. You take one step onto the street. That step is your brain's world. Now imagine someone tells you calmly that the thing you're trying to understand is not across the street and not across the city, but across the entire continent. Not just far. So far that your sense of far becomes meaningless. That is what cosmic scale does to us. We don't just underestimate it. We underestimate it so severely that our inner compass snaps, and we don't even feel it snap. And once that happens, even a perfectly true fact can sound false. That's why scale is the hidden enemy in astronomy, because astronomy is the science of things we cannot touch. Separated by distances our biology refuses to hold. And here's the part that lands personally. When you look up, the sky feels like a ceiling. It feels close enough to point at. And that feeling isn't stupidity, it's design. Your mind is trying to keep your world stable. If the sky felt like what it really is, an opening into a depth so extreme that even the fastest signals in nature take years to cross it, you wouldn't feel wonder first. You would feel something colder, something like vertigo. So your brain does the only thing it can do. It turns the universe into a picture you can survive. But the universe is not a picture. So how did we escape the trap? We did something rare in human history. We admitted our senses were not enough, and we built instruments and mathematics that could outvote our intuition. This is where astronomy becomes more than stargazing. It becomes a discipline of humility. Because the first step toward cosmic truth is not a telescope, it's distrust. Distrust of what looks right. Long before we had the James Webb Space Telescope, long before NASA and ESA were mapping the cosmos in exquisite detail, astronomers realized something brutal. If we rely on appearance, we will be fooled. So they built methods that don't care how things look. They used geometry. They used timing. They used the predictable behavior of light. They began with what was closest, where measurement was possible. Then they built outward, step by step, like climbing a ladder into darkness, a structured scale ladder. Not because it was elegant, because it was the only way not to drown. Here's the strange part. We can't measure the whole universe in one move. We can't stretch a tape measure to the moon, let alone to the stars. So astronomy uses a chain of methods, each one anchored to something we can verify. For nearby objects, we use direct techniques, methods grounded in geometry and motion. For farther objects, we use calibrated signals, patterns in light that act like cosmic mile markers, and each rung depends on the one below it being correct. This is why astronomers obsess over cross-checks, because one small error at the bottom becomes a catastrophic error at the top. A tiny distortion becomes a monstrous lie, and that's why debates over measurement matter. That's why scientists argue over distances, over expansion rates, over calibration. Not because they enjoy conflict, because the scale of the universe is not a philosophical question. It is a measurable physical reality. And if we mismeasure it, we misinterpret everything. The age of stars, the structure of galaxies, the history of the cosmos itself. Einstein understood something like this when relativity rewired how we think about space and time. Edwin Hubble faced it when observations forced the universe to expand in our minds. And today, teams using instruments like Webb and other major observatories still live inside the same battle, Reality is enormous. Our intuition is small, so we build ladders, and we climb anyway. So what have we actually uncovered here? We've uncovered the real villain. It isn't darkness, it isn't distance, it isn't even emptiness. It's the human mind trying to compress the cosmos into a size that feels safe. Our intuition was never meant to hold light years. Our instincts were never meant to feel billions. Our imagination was never meant to picture a universe where nearby can still be unreachable. And yet, we measure it, we map it, we translate the impossible into something we can speak aloud, not perfectly, not without error bars, not without argument, but with enough precision to build a coherent scale, one rung at a time, and that changes something inside us, because it means the universe is not beyond understanding, it's beyond intuition, which is a very different thing. But this creates a bigger problem. If our minds distort scale so easily, then the first rung of the ladder has to be unforgiving. Because if we start with a false baseline, everything above it fractures. So we have to begin with something that feels familiar, and then reveal how even that familiar thing is not what we think. We have to begin with our home, with Earth, because Earth is the only cosmic object we feel like we understand. Except, Earth is smaller than we think, and once we set that baseline correctly, the rest of the universe begins to expand in our minds like a door opening into a storm. We keep reaching for the universe. We talk about Mars, we talk about Saturn, we talk about galaxies, but there's a problem that hides in plain sight. If we misunderstand the size of Earth, then every distance we think we understand beyond Earth is already corrupted. The entire cosmic story becomes warped at the very first sentence. And the terrifying part is how easy it is to get wrong, because Earth feels huge when we're inside it. It feels endless when we're driving for hours, when mountains block the horizon, when oceans stretch without a seam. But when we step back, when we force ourselves to measure instead of feel, Earth becomes something else. Not infinite, not even close. It becomes a baseline. And baselines have a brutal rule. If the baseline is wrong, everything above it collapses. So before we talk about the solar system, before we talk about light years, we have to do something almost uncomfortable. We have to look at our home and admit it is smaller than our instincts insist. Our brains didn't evolve to understand a globe. We evolved on a surface that looks flat, a surface where the horizon is always a few kilometers away, a surface where we can walk for hours and still feel like we haven't moved far at all. So Earth tricks us. It lets us treat the world like an endless plane, a stage that goes on forever. Except Earth is not an endless plane. It's a sphere with a known size. Earth's diameter is about 12,742 kilometers, about 7,918 miles. Say that slowly, and it still doesn't land, because numbers alone don't create meaning. We need comparison. We need something we can hold in our hands. And this is where the story cracks open, because the moment we convert Earth into an everyday object, our intuition begins to fracture. Let's do one clean, brutal scale. If Earth were the size of a standard classroom globe, about 30 centimeters, wide, about 12 inches, then the entire planet, every city, every ocean, every war, every civilization, fits on something you can lift with one hand. In that scale, a commercial airplane flying at cruising altitude isn't soaring through the sky. It's hugging the surface like a thin layer of dust. The highest mountains become tiny roughness on a painted shell. And the atmosphere, the thing that keeps us alive, the thing we treat like a vast open ceiling, becomes a fragile skin. Not thick, not generous. A thin boundary wrapped around a small world. And this creates a new problem. Because once Earth is small, we start asking a different question. If Earth is this limited, then what does space actually mean? Where does up stop being Earth and start becoming the true void. Earth's circumference, the distance around the equator, is about 40,075 kilometers, about 24,901 miles. That's enough to circle the planet. But we don't experience Earth as a loop. We experience it as a surface. We experience it as forward. So our minds store Earth as a feeling, days of travel, weeks of distance, a sense of far away. But that's not measurement. That's psychological weight. And psychological weight grows faster than real distance. A long drive feels enormous because it stretches our patience. A flight feels cosmic because it detaches us from the ground. A map feels infinite because it's full of names we've never visited. But Earth doesn't care how the trip felt. Earth has a circumference, a diameter, a measurable size. And once we accept that, we can finally place the next object in the story where it truly belongs. The moon. Most people picture the moon as nearby. It hangs above us like a lamp. It looks close enough to touch with a fingertip. But here is the strange part. The average distance from Earth to the moon is about 384,400 kilometers, about 238,855 miles. That's not just a little farther than the atmosphere. That distance is so large that if we scaled Earth down to a basketball, the moon would be a tennis ball, and it would be about 7 to 8 meters away, about 23 to 26 feet. Not across the room, across the entire space between rooms. And what fills the space between the basketball and the tennis ball? Almost nothing. No glowing mist, no soft haze, just emptiness. This is why the Apollo missions still feel unreal. NASA didn't just send humans up, they sent humans across a gulf of vacuum so wide that Earth and the moon stop feeling like neighbors and start feeling like separated islands in a black ocean. And the emptiness between them is the first time our intuition truly starts to panic, because if the moon is that far, then our everyday idea of space travel is already shattered. Picture this. We put a basketball on the ground outside your home. That's Earth. Then we walk away 8 meters, about 26 feet, and place a tennis ball. That's the moon. Now look at the space between them. That empty gap is the Earth-Moon distance, scaled down. And here's the disturbing detail. In real life, we could fit every planet in our solar system into that gap, if we ignore the rings. That's how much room there is between Earth and the moon. Our instincts never show us that. Our instincts show us a moon that feels attached to our sky. But in reality, even our nearest celestial neighbor is separated by a silence so wide that it changes what near means. And that's when another misconception appears. Because most people assume the satellites we use every day are close to the moon. They aren't. Not even remotely. When we hear satellite, we imagine something far above the clouds, far above Earth, drifting out, in the void. But most of what we call space infrastructure is still clinging tightly to Earth. The International Space Station orbits at roughly 400 kilometers above Earth, about 250 miles. That sounds high, but on a classroom globe, that altitude would be less than the thickness of a coat of paint. So, when we say astronauts in orbit, we are not talking about travelers deep in space. We are talking about humans skimming the edge of home. Even geostationary satellites, used for communications and weather, sit at about 35,786 kilometers above Earth, about 22,236 miles. That is far compared to airplanes, but compared to the moon, it's still not even 1/10 of the way there. And GPS satellites, which quietly shape modern life, orbit at around 20,200 kilometers, about 12,550 miles. Our technology feels like it's out there, but it's still in Earth's grip, still inside Earth's immediate neighborhood, still inside the first shallow layer of the cosmic ocean. And this is why scale matters, because once we get Earth right, we finally see a truth that is almost unsettling. Even what we call space is barely a step away from the ground. And when you look up tonight, when you see the moon and feel how close it seems, your brain will try to compress it again. It will try to bring it down to a size that feels safe. But if you hold this scale in your mind, something changes. You realize the night sky isn't a ceiling, it's a direction that opens into distances so extreme that even the moon, that bright, familiar face, is not near in human terms. It's simply the nearest proof that our instincts were never built for the truth. So why do illustrations keep getting this wrong? Why do posters line planets up like beads? Why do diagrams show the moon just beyond the atmosphere? Because accurate scale is visually impossible on a single page. If we draw Earth large enough to see continents, then the moon has to be drawn so far away it disappears off the paper. If we draw the Earth-Moon distance correctly, then Earth becomes too small to see. So illustrations compromise. They compress. They bend reality. Not because artists are careless, because our eyes demand a picture, and scale refuses to be pictured. This is why we need a structured ladder of scale, not a single image, not a single wow shot, a ladder, where each rung prepares our minds for the next. Because the universe is not one leap, it is a series of expanding shocks, and Earth is the first shock we have to accept. So what did we do in this step? We did something simple and deeply unsettling. We took Earth, our most familiar object, and measured it instead of feeling it. We learned that Earth is large enough to hold everything we've ever loved, but small enough to fit in our hands as an object. We learned that the atmosphere is thin, the orbits are close, and the moon is separated by a gulf of emptiness. And once we accept that, we finally understand the rule we'll need for everything ahead. Scale is not what we imagine. Scale is what survives measurement, and this is why our baseline matters, because Earth is the ruler we will use to measure the next rung, and the next rung is where the real desert begins. But this is where everything changes, because if Earth is this small and the moon is this far, then what happens when we step beyond the Earth-Moon system? What happens when we try to place the planets on the same scale? The distances stop feeling like travel. They start feeling like abandonment. Because the solar system is not a busy neighborhood. It's a vast local desert, with worlds scattered like dust grains across an emptiness that swallows meaning. And once we lay those distances out honestly, we'll see why, even at the fastest speeds we've ever achieved, most of the solar system remains effectively out of reach. And that's when the true scale ladder starts to climb. We tend to picture the solar system like a family portrait, a warm little lineup, the sun in the center, planets spaced neatly like beads on a string. But that picture is a lie our intuition tells us to stay comfortable. Because the real solar system is not a busy neighborhood, it's a desert. A local desert so wide and so empty that it changes what distance even means. And here's the disturbing part. There are no stars out there to guide our eyes, no streetlights, no landmarks, just a black silence where even the biggest planets are isolated. So, if we're going to understand the true scale of the universe, we have to survive this step first. We have to confront the first region where our instincts truly collapse. Because the solar system is where far stops being emotional and becomes mathematical. And once we see it clearly, a deeper question opens. If this is only our local neighborhood, what waits in the darkness between stars? From Earth, the sun looks like a coin of light. The planets look like bright dots, so our mind compresses them. It squeezes them together into a tidy mental model. But scale doesn't care about how something looks from the ground. Scale cares about distance. And in the solar system, distance is the main character. So astronomers use a unit designed for this place, because kilometers and miles become exhausting too fast. They use something simple. They use astronomical units. One astronomical unit, one AU, is the average distance from Earth to the Sun. That's about 149,600,000 kilometers, about 92,960,000 miles. 1 AU, a single step on the ladder. And that number is already too large for the human nervous system to feel, so we translate it into something our bodies can understand. Light takes about 8 minutes and 20 seconds to cross 1 AU. That means when we look at the Sun, we are not seeing it now. We are seeing it 8 minutes in the past. That's not philosophy, that's physics. And once we accept that, the solar system starts to unfold like something ancient and cold. Here's where the story cracks open. The planets are not arranged like a diagram, they're scattered. They're separated by emptiness so vast that our minds try to look away. Earth sits at about 1 AU. Mars is around 1.5 AU from the Sun. Jupiter, this giant world, lives at roughly 5 AU. Saturn drifts at about 9.5 AU. Uranus is around 19 AU. Neptune is around 30 AU. And that spacing matters, because when people imagine travelling through the solar system, they imagine moving between worlds. But in reality, most of the journey is not between planets, it's through nothing, through black, empty volume, through distances so large that even light, our fastest messenger, starts to arrive late. And that's when a new problem appears. If light itself needs minutes and hours to cross our own neighbourhood, what does that say about the universe beyond it? We can feel the scale of the solar system more honestly by watching what happens to light. Sunlight reaches Earth in about 8 minutes and 20 seconds. To Mars, sunlight takes roughly 12 minutes on average, sometimes more, sometimes less, depending on where Mars is in its orbit. To Jupiter, it's about 43 minutes on average. To Saturn, roughly 1 hour and 20 minutes. To Uranus, about 2 hours and 40 minutes. To Neptune, about 4 hours. And out at Pluto, far beyond the main planetary path, sunlight can take around 5.5 hours. So when we speak across the solar system, we are not speaking in real time. We are sending messages into a delay, a controlled, measurable delay that grows into something almost haunting, because it means distance isn't just space, it's separation in time. And once we understand that, we stop romanticizing the solar system. We start respecting it, because it's not a playground, it's a geometry of isolation. Imagine this. We shrink the solar system into a city you know. We place the Sun in the centre of town, and we place Earth 1 metre away, about 3 feet, a small step, a familiar distance. Now Mars is another half metre beyond that, still walkable. But Jupiter is suddenly 5 metres away, about 16 feet, across a wide room. Saturn is nearly 10 metres, about 31 feet, across the length of a house. Uranus is about 19 metres, about 62 feet, across a small street. Neptune is 30 metres, about 98 feet, almost a full building length away. And here's what matters. Most of that city is not landmarks, it's empty pavement, it's silence. So when we picture the solar system as a cluster, we're mentally erasing the thing that defines it. The emptiness is the structure. And that emptiness is why space travel becomes so brutal. We have built spacecraft that leave Earth behind and never come back. NASA's Voyager probes, launched in the late 1970s, became the first human-made objects to travel into interstellar space. They move at tens of thousands of kilometers per hour, tens of thousands of miles per hour. That sounds monstrous, it sounds like escape. But here's where the universe humiliates us. At those speeds, a spacecraft could cross an entire continent in minutes. It could cross an ocean before you finish a cup of coffee. And yet, even moving that fast, it takes years just to reach the outer planets, decades to reach the far edge of the Sun's protective bubble. If a Voyager-like journey had started when ancient pyramids were still young, it still wouldn't have crossed even a fraction of the distances that begin beyond our local neighbourhood. This is why the solar system is a desert. It punishes our instincts about travel, and it forces us to measure honestly, and then we reach a name that still stirs emotion: Pluto. People argue about Pluto as a planet, but that argument hides the deeper truth. Pluto matters whether we call it a planet or not, because Pluto sits in the Kuiper Belt, a region of icy bodies beyond Neptune. Pluto is locked in a stable rhythm with Neptune, an orbital resonance that keeps them from colliding. It's a reminder that gravity isn't just a force, it's choreography. Pluto also isn't alone. It's part of a population, many worlds, many frozen objects, shaping one another subtly over billions of years. And Pluto has a companion, Charon, large enough that the two orbit a shared point in space, like a paired system, not a simple moon and planet. So Pluto isn't a forgotten snowball. It's a signpost, a marker showing us that the solar system doesn't end where our childhood diagrams stopped. It extends into a frontier of objects we're still mapping, still counting, still trying to understand. And that opens the next layer of the desert. Beyond Neptune, from roughly 30 to 50 AU, the Kuiper Belt spreads out, a cold region of icy bodies, dwarf planets, fragments, remnants from the solar system's formation. This is where objects like Pluto live, and it matters because it changes the boundaries of what we mean when we say the solar system. If we define the solar system only as the 8 major planets, we miss the truth. The truth is that our system has structure beyond the planets, a thickening of debris and distant worlds, a shadowy ring where the sun is still bright enough to cast light, but too far away to feel warm. And then, even that isn't the end, because farther out, astronomers see evidence of something even more extreme, something we haven't photographed directly, but infer from the paths of comets, like footprints leading into darkness. This is where we have to speak carefully. The Oort cloud has not been directly imaged, but astronomers infer it as a vast reservoir of icy bodies, far beyond the Kuiper Belt, because long-period comets arrive from every direction, like visitors falling in from a spherical shell. Estimated distances vary. Some models place its inner region thousands of AU away. Some place its outer reach as far as 100,000 AU, approaching a couple light years. So we don't treat it like a confirmed photograph. We treat it like a strong inference from consistent evidence. And even as an inference, it tells us something chilling. The solar system may be far larger than the region we can easily visualize, not because it's filled with planets, but because the sun's gravity still whispers, even across staggering distances. And that leads to the question that defines this entire chapter. How far does the sun's influence actually reach? There are different ways to define the edge of the solar system. One edge is physical shielding. The sun blows a stream of charged particles, the solar wind, that inflates a protective bubble around us. Voyager 1 and Voyager 2 measured the boundary of that bubble. They crossed into interstellar space after traveling far beyond the planets, reaching the region astronomers call the heliopause, roughly over 100 AU from the sun. That's already staggering, but gravitationally, the sun reaches farther. Gravity doesn't stop at the heliopause. It fades, it weakens, but it continues, out into the realm where comets may sleep for billions of years, barely bound to our star. Out toward distances where the galaxy's tides begin to compete, where passing stars can disturb the farthest objects. Astronomers estimate the sun's gravitational dominance extends out toward that Oort cloud scale, possibly approaching 1 to 2 light-years in reach, depending on what boundary we're talking about. And now we can finally say it out loud. The solar system is not the 8 planets. It's a layered structure, a bright inner zone, a planetary region, a belt of frozen debris, a cloud inferred from comet paths, and a fading gravitational grip that dissolves into the galaxy. And this creates a deeper mystery, because when the sun finally lets go, what's waiting beyond that last thin boundary? And if you could stand out there, far beyond Neptune, far beyond Pluto, and you turned around to look back, you wouldn't see the solar system. You would see a bright star, a single point of light, one among countless others. And that's when the emotional weight hits. Our entire home system, everything we've ever touched, does not end with a wall. It ends with distance. It ends with emptiness. It ends with a slow surrender of gravity. And once we accept that, the next step is unavoidable. Because beyond the sun's reach, the desert doesn't get gentler. It becomes truly empty. So here's what this rung of the ladder gives us. We learned the solar system isn't a compact set of planets. It's a scale problem. A system defined by vast separations, delayed light, and expanding emptiness. We learned why AU exist, because our usual units collapse under the weight of these distances. We learned that even sunlight becomes late. We learned that Pluto isn't a punchline, it's a marker at the edge of a deeper frontier. We learned that the Kuiper belt extends the system, and that the Oort cloud, strongly inferred from comet behavior, may extend it far beyond what we can picture. And we learned that the sun's influence fades in layers. First it's wind, then it's gravity, then silence. But that's not the whole story, because this desert is still local. It still belongs to one star, and the universe has a much colder gap ahead. Beyond the solar system, there are no comfortable units left. AU stopped being useful, because now the distances aren't between planets, they're between stars, and the nearest star is not a little farther. It's separated from us by a gulf so wide that our entire solar system becomes a tiny island, drifting alone. To describe that gap, we need a new unit, a unit that sounds familiar, but hides a terrifying truth, a light year. And once we cross into that idea, once we step into the interstellar gap, we'll see what empty really means. We survive the solar system. We watch the planets spread out into a vast local desert, and we learn that even sunlight arrives late. But now we reach a boundary that feels different. Because beyond the sun's fading influence, the emptiness stops being space between planets and becomes something colder. It becomes the space between stars. And the terrifying part is this. In that gap, there is no comforting scale left, no familiar unit, no sense of almost there, no visual anchor, just distance so extreme that our instincts quietly collapse. This is where our story stops feeling like travel and starts feeling like separation. And once we name the unit that defines this gap, we'll understand why interstellar space isn't just far. It's far in a way that rewrites what nearby even means. Here is the problem. The phrase light year sounds like time. It sounds like a calendar, something we can wait through. But a light year is not time, it's distance. It's the distance light travels in 1 year, moving at about 300,000 kilometers per second, about 186,000 miles per second. That distance is about 9.46 trillion kilometers, about 5.88 trillion miles. And now we feel the trap, because when we hear 4 light years, our brains latch onto the 4, but the real meaning is the rest of the phrase. Light year is basically the universe telling us even the fastest thing nature allows needs years to cross the gap. And that's when the nearest star stops feeling near. The closest star to us, after the Sun, is Proxima Centauri, and it's about 4.25 light years away. That sounds like a small number, but remember what it means. 4.25 light years is roughly 40 trillion kilometers, about 25 trillion miles. So even the nearest star is separated from us by a gulf that swallows ordinary language, and this creates a bigger problem, because when we look at the night sky, we don't see a gulf, we see a crowd. We see stars sprinkled everywhere, close enough to feel like they share the same ceiling, except they don't. They're scattered through a volume, and the volume is mostly empty. Imagine this. We shrink our entire scale down until the distance from Earth to the Sun, 1 astronomical unit, becomes 1 centimetre, less than half an inch, a tiny step. Now we try to place the nearest star on the same scale. Proxima Centauri would not be across the room. It would be about 2.7 kilometres away, about 1.7 miles. That's like putting our sun on one street, and the nearest star on the far side of a city, and everything in between, almost nothing. No planets, no bright dust lanes, no glowing fog, just emptiness. And this is where our intuition fractures, because we realize something uncomfortable. Our solar system is not one neighborhood among many, it's one isolated point in a dark ocean, with the next point shockingly far away. So why does the sky look crowded? Because we're standing inside it. We're looking through a huge depth of space, and our eyes compress it into a flat dome. But when astronomers measure local stellar density, how many stars exist in a given volume near the Sun, the number is astonishingly low. Near our region of the Milky Way, estimates are around 0.004 stars per cubic light year. That means, on average, the stars are separated by multiple light years, not meters, not kilometers, not even astronomical units, light years. So the night sky looks like a glittering crowd, but the reality is closer to a few distant fireflies in a vast, empty field, each one separated by distances so large that the darkness between them becomes the dominant feature. And that is where interstellar travel turns from engineering challenge into something harsher. It becomes a scale problem. We can build fast machines. NASA has launched spacecraft that move tens of thousands of kilometers per hour, tens of thousands of miles per hour. Voyager 1, for example, is moving around 17 kilometers per second relative to the Sun, about 38,000 miles per hour. That feels violent, that feels unstoppable, but this is where everything changes. At that speed, Voyager would take on the order of 73,000 years to reach Proxima Centauri, if it were headed that way. 73,000 years. That's not a trip, that's a geological event. That's longer than all of recorded human history. When humans were painting on cave walls, when agriculture didn't exist, when cities weren't even a dream, Voyager would still be traveling through darkness. And even if we imagine the kind of speed humans have actually achieved on a crewed mission, Apollo-era speeds, credible estimates still, land in the tens of thousands of years to reach the nearest star. So the problem isn't that we're slow. The problem is that space is too big to conquer with familiar ideas of speed, and that makes the emptiness itself feel different. Because now, we're not talking about emptiness as a background. We're talking about emptiness as an obstacle. Inside the solar system, emptiness already felt enormous. But interstellar space is emptiness with a new flavour. There are no planets as stepping stones. No warm central star dominating the sky. No sense of being inside a system. It's a region where even light years become the basic unit of thought, and that creates a strange emotional shift in us, because we realize the universe isn't built like a map with towns. It's built like a wilderness with a few distant campsites, separated by nights that never end. And now the story gains another layer. Because while we're imagining this gulf as something we might one day cross, we forget something even more disturbing. We are not standing still. Even when we feel still, we're moving. The Sun orbits the center of the Milky Way, carrying Earth and every planet with it. NASA describes our solar system moving at around 720,000 kilometers per hour, about 450,000 miles per hour. And at that speed, it still takes about 230 million years to complete one orbit around the galaxy. 230 million years. When the Sun last completed a full lap, The continents on Earth were in different places. The planet's life was in a different chapter. So the interstellar gap isn't just something out there. We're already moving through it, quietly, constantly, while we live our ordinary lives. And this is where the scale becomes almost philosophical, because it means our home is not fixed. It's a moving point in a dark, rotating system, a small vessel of gravity and light, drifting through a much larger structure. And if you step outside tonight and look at the stars, you're not looking at a scene happening now. You're looking at delays, light that has been traveling, light that crossed emptiness for years, sometimes far longer, before it reached your eyes. So that calm, still sky you're seeing is actually motion and distance made visible, a silent announcement that the universe is not built for intuition, it's built for measurement. So what have we learned on this rung of the ladder? We learned that the solar system's desert was only the beginning, because the space between stars is a different category of empty. We learned what a light year really is, not time, but distance, trillions of kilometers, trillions of miles, a unit born from necessity. We learned that Proxima Centauri, the nearest star, is still 4.25 light-years away, so far that even our fastest probes would take tens of thousands of years to arrive. We learned that our local region is not packed with stars. Stellar density near the Sun is low, and that's why the darkness dominates the volume. And we learned something quietly unsettling. Even as we speak, we're drifting through the galaxy at hundreds of thousands of miles per hour, and still it takes hundreds of millions of years to go around once. But that's not the whole story, because if the interstellar gap is this vast, then what happens when we zoom out far enough to see what those stars belong to? The next rung is where the universe stops looking like scattered dots and becomes a structure, a galaxy. And once we step inside the Milky Way, we'll discover something even more disturbing. A galaxy is not a dot. It's a living architecture of motion, gravity, and time. When we look up, the Milky Way looks like a stain of light, a pale river, a soft wound across the darkness. It feels decorative, it feels distant, it feels like background. But that's the illusion, because that band is not out there. It's us looking through our own galaxy, through a structure so large that our minds flatten it into a strip, just to survive seeing it. And here's the disturbing part. A galaxy is not a dot. It is not a single object. It is an architecture made of stars, dust, gas, magnetic fields, and gravity, all moving at once. And if we keep treating it like a dot, we will misunderstand everything that comes next. So we have to do what astronomy always forces us to do. We have to stop trusting what it looks like and start asking what it is. There's a cruel limitation built into our situation. We live inside the Milky Way, which means we can't step outside it and take a clean picture. NASA says it plainly. From inside, we cannot photograph our galaxy's spiral structure the way we can photograph other galaxies. So how do we know what it looks like? We infer it, we map it, we measure the positions and motions of stars and gas, and we reconstruct the larger shape, like someone learning the shape of a forest by walking through it in the dark. And that reconstruction reveals something humbling. Our galaxy is a barred spiral, a central bar of stars with spiral arms unwinding outward. Not a dot, a living, rotating system. And when we finally accept that, a single number hits us like gravity. The Milky Way is roughly 100,000 light-years in diameter. Say that slowly. 100,000 light-years. A light-year is distance. So this is not a timeline. It is a measurement of width. It means if light started at one edge of our galaxy and raced across at nature's maximum speed, it would need about 100,000 years to reach the other side. And this creates a new problem, because we're tempted to picture that distance as a flat circle. But the Milky Way isn't a flat drawing. It has thickness, it has depth, and the thickness is where our intuition starts to fracture again. NASA's Webb scientists describe disk galaxies as layered, a thick disk and a thin disk. For the Milky Way, Webb notes a thick disk around 3,000 light-years in height and a thin disk roughly 1,000 light-years thick. So we can feel the shape, a structure about 100,000 light-years wide, but only about 1,000 light-years thick in the thin disk where many stars live. It's like a vast cosmic blade, a disk with a shallow vertical layer stretched across a width so enormous our minds can't hold it. And in that disk, somewhere not special, not central, we're moving. Our solar system is about 26,000 light-years from the galactic center, not near the middle, not near the edge, somewhere in the outer regions of the disk in a spiral arm neighborhood, often called the Orion Arm or Orion Spur. And the center we orbit isn't just a bright spot, it's a region dominated by the supermassive black hole known as Sagittarius A star, about 26,000 light-years away from us. So when we look toward the brightest, thickest part of the Milky Way, we're looking toward the deep gravitational heart of the system. But here's the strange part. Even that heart is not stationary in any emotional sense, because the whole galaxy is rotating, and that rotation has a time scale that makes human history feel like a blink. NASA explains that it takes about 250 million years for the Sun, and Earth with it, to complete one orbit around the Milky Way's center. 250 million years. The last time our solar system was in this same region of its orbit, the early dinosaurs were just beginning to appear on Earth. Mammals were small and hidden. No humans, no cities, no language as we know it. Our entire recorded history, every empire, every revolution, every library, every satellite, fits into a fraction of that single galactic lap. So when we say we live in the Milky Way, we're not describing a place that holds still. We're describing a moving trajectory, a long orbit through a structure we can barely picture. And this raises another question. If the galaxy contains that many stars, how many are we talking about really? Astronomers estimate the Milky Way contains roughly 100 billion to 400 billion stars. That range isn't carelessness, it's honesty. NASA explains the estimates vary because different models make different assumptions, like what the average star mass should be and how to account for faint stars that are hard to detect. And now we face the problem again. Billions doesn't land in the human body, so we translate it into something we can feel. The labor time conversion, counting stars until the universe runs out of patience. If we tried to count 100 billion stars, one per second, without stopping, it would take over 3,000 years. If the true number is closer to 400 billion, it becomes over 12,000 years. That's longer than the entire span of written history. So the Milky Way isn't just large, it's large in a way that breaks the idea of counting at all, which is why we don't count stars one by one. We do something colder. We sample, we survey, we infer. Modern astronomy uses vast sky surveys to measure positions, distances, and motions. ESA's Gaia mission, for example, produced a star catalogue with high-precision measurements for nearly 1.7 billion stars in an early major release. That's not the whole Milky Way. It's a massive slice of it, enough to reveal structure, streams, and motion with disturbing clarity. And Gaia's later releases reach into the scale of billions of sources across the sky. This is how we build the map. We measure how stars shift against background objects. We measure how their light changes. We measure how they move. Then we stitch those measurements into a model of the whole. And when we do, we find a galaxy that is not a static spiral painting. It has arms, but the arms are not what most people think they are. For a long time, the simplest idea was also the most tempting. Spiral arms are made of the same stars, fixed in place, like permanent lanes. But that idea collapses under a brutal reality. Different parts of the galaxy rotate at different speeds. If spiral arms were made of fixed material, they would wind tighter and tighter over time until the pattern was destroyed. This is called the winding problem. So astronomers developed a deeper explanation, a powerful one. The spiral arms behave like density waves, regions where stars and gas crowd together temporarily, like a traffic jam moving through a highway. Stars move through the spiral pattern. They enter a region of higher density, gas compresses, star formation can ignite, then they drift out again. The pattern persists, even though the stars themselves do not stay in the arm forever. That is why the arms can exist for long timescales without winding into a knot. And now we see the galaxy for what it is. Not a picture, a process, a rotating system with waves of density, regions of birth, regions of dust, and long gravitational rhythms. Imagine this. We're above a city at night, looking down at a highway. Most of the road is moving. Cars flow steadily. But then we hit a traffic jam. Suddenly, there's a bright, dense knot of headlights. Cars enter the jam. They slow, they bunch up, then they exit, and speed up again. The traffic jam is not made of the same cars. It's made of a pattern. That's what spiral arms are like. Not permanent objects. A pattern of crowding moving through a rotating disk, compressing gas, shaping star formation, and giving the galaxy its haunting pinwheel appearance. And that creates a deeper mystery. If the Milky Way is this enormous and structured, how fast are we moving through it? NASA notes our solar system moves around the Milky Way at about 450,000 miles per hour, about 720,000 kilometers per hour. That number sounds violent. At that speed, we could travel from New York to London in about 28 seconds. We could reach the moon in about half an hour. But even at that speed, NASA explains it still takes around 230 million years for one complete trip around the galaxy. So the galaxy doesn't care about our speed instincts. It forces us to think in different units, different time, different meaning. And when you look up at that milky band tonight, you're not seeing decoration. You're seeing the edge-on glow of a structure you're embedded inside. You are inside a rotating disk with hundreds of billions of stars. Inside a thin layer where star clouds drift and collapse. Inside a system so wide that even light needs 100,000 years to cross it. That band in the sky is not far away. It's the shape of the place we live. And once you feel that, a quiet question appears. If our galaxy is this vast, is it alone? So what have we earned on this rung of the scale ladder? We stopped treating the Milky Way like a dot. We saw its width, about 100,000 light years. We saw its layered thickness, thin disk around 1,000 light years, thick disk around 3,000 light years. We placed ourselves about 26,000 light years from the center. We faced the star count, roughly 100 to 400 billion, measured through models and surveys because direct counting is impossible. And we understood the arms, not as fixed objects, but as density waves that solve a fundamental problem of rotation. We learned that a galaxy is not an image, it's a machine of motion. But this is where the universe has one more twist. Because once we finally understand our own galaxy as an island, we naturally ask what every astronomer eventually has to ask. How many other islands are out there? Because the Milky Way is only one galaxy. And once we grasp its true scale, something unsettling becomes inevitable. If one galaxy can hold hundreds of billions of stars, then the night sky is not just a canopy of stars, it's a window into a much larger ocean of galaxies. And when we step beyond our island, we're forced to face the next reality. Galaxies are not alone. They come in groups, they come in clusters, and the nearest great neighbor, Andromeda, has been waiting in the dark this whole time. For most of human history, the sky told us a single, comforting lie, that every light we see belongs to us, that the Milky Way is the whole stage and everything else is just fog. And then, in the early 20th century, astronomers pointed a telescope at a pale smear in Andromeda, and the smear refused to stay small, because hidden inside it, they found something that should not exist, a star that pulsed like a heartbeat, predictably, measurably, like a countdown, and with that rhythm the universe shattered, not with an explosion, with a number, a distance so large it destroyed an entire worldview. But here's the strange part. That discovery didn't just reveal that other galaxies exist, it revealed something colder. We are not in a universe, we are in a neighborhood, and neighborhoods have borders, and crowds, and gravity, and hidden mass we cannot see. And that is where the real story begins. We tend to imagine space like an ocean with a few ships scattered across it, but that picture is wrong. Galaxies are not lone wanderers. They gather, they orbit, they collide. They form families, bound together by gravity, moving through darkness like a slow, ancient migration. NASA describes these groups and clusters as building blocks of the universe, collections of galaxies held together by gravity. So when we look up, we're not seeing isolated lights. We're seeing structure, and once we accept that, everything changes. Because if galaxies come in groups, we have to ask, how many galaxies are near us right now? And how far does near really go? Astronomers call our neighborhood the local group. Not a poetic name, a clinical one. Because this isn't mythology, this is cartography. NASA explains that the Milky Way sits with over 50 other galaxies in this local group, ranging from small dwarf galaxies to Andromeda, our nearest large neighbor. And NASA's Imagine the Universe project notes that the local group stretches across nearly 10 million light-years. 10 million light-years. That number doesn't feel real, so we have to do what our intuition cannot. We have to translate it into human meaning. A light-year is the distance light travels in 1 year. So 10 million light-years is 10 million years of light moving at the fastest speed anything can carry information. If the local group were a city, we wouldn't be standing at the center. We'd be standing inside one apartment building, on one floor, in one room, and calling it home. And the local group isn't even the whole city. It's only the first block. The largest presence in our local group is Andromeda. NASA's Hubble mission describes Andromeda as about 2.5 million light-years away. Close by cosmic standards. Close. Listen to what that means. 2.5 million years ago on Earth, our ancestors were not building cities. They weren't writing. They weren't farming. They were barely beginning to walk the planet with anything like human awareness. And the light entering our telescopes tonight left Andromeda when that ancient world was still waking up. That's not just distance. That is time embedded in light. And if we try to cross that gap with machines instead of photons, NASA's Voyager probes travel on the order of tens of kilometers per second, fast enough to cross a country in minutes, but meaningless against intergalactic space. At that kind of speed, a journey to Andromeda would take roughly 43 billion years, longer than the age of the universe, which NASA places at about 13.8 billion years. So Andromeda isn't merely next door, it is next door in the way continents are next door, visible across an ocean, unreachable without a new kind of travel. And that fact creates a bigger problem, because if Andromeda is only one neighbor, what kind of place is the universe if even our nearest giant galaxy is basically unreachable? A century ago, this wasn't obvious. In 1920, astronomers publicly argued about whether spiral nebulae like Andromeda were inside the Milky Way, or entire galaxies far beyond it. And then Edwin Hubble's observations of a Cepheid variable star in Andromeda helped settle it, showing that the universe contained galaxies beyond our own. NASA commemorates that discovery as the moment a new universe opened up. It wasn't a romantic revelation, it was unsettling, because it meant the Milky Way wasn't the universe, it was a single galaxy among many. And once we accept that, we're forced to face the next scale. Not stars, not planets, collections of galaxies. The local group is a group, a modest gathering. NASA describes galaxy groups as typically holding 100 or fewer galaxies. But then there are clusters. Clusters are not gatherings. Clusters are crowds. NASA explains that galaxy clusters contain hundreds to thousands of galaxies, and it gives a concrete example: the Coma cluster, with over 1,000 galaxies stretching over 20 million light-years across. 20 million light-years. That is twice the diameter NASA gives for the entire local group. So our local group isn't a metropolis. It's a small town on the edge of a much larger civilization of galaxies. And that raises a question that refuses to go away. What holds these immense structures together? Because when you pack thousands of galaxies into one region, the math becomes disturbing. The visible matter isn't enough. This is where the universe turns cold. Astronomers learned that galaxy clusters behave like they're heavier than they look. NASA notes that clusters contain not only galaxies, but also hot gas, and abundant dark matter, an invisible substance scientists know must exist, but have not identified. And NASA's Roman Space Telescope science pages explain one of the clearest lines of evidence: gravitational lensing. When massive, clusters bend and warp the light of galaxies behind them. The amount of warping reveals the total mass, and the visible matter is not enough to produce the observed lensing. Dark matter provides the surplus gravity. ESA has shown the same reality through Hubble observations, describing dark matter as the source of extra gravity that holds galaxy clusters together. So the universe teaches us a brutal lesson. Light is not an honest measure of mass. A cluster can glow and still be missing most of its weight, which means when we map the cosmos, we are not just mapping what shines, we are mapping what pulls. And that changes the meaning of structure. Picture this. We're standing at night on a coastline. Across the water we see city lights. One cluster of lights is close, our own shoreline. Another cluster is distant, Andromeda, across the dark. Now imagine that beneath the water, hidden, silent, there are massive underwater ridges shaping the waves, guiding the currents, controlling where the lights can gather. We can't see those ridges directly, but we can see what they do to everything moving above them. That is dark matter, not a story, not a guess. An invisible gravity revealed by what it bends and what it holds together. And now, let's make it personal, just once. You're not watching this from the center of anything. You're sitting inside one galaxy, inside a small group, on the edge of larger structures, in a universe where gravity is doing most of its work in darkness. That should feel disturbing, because it means the cosmos is not arranged for our convenience. It is arranged by mass, seen and unseen, and we only understand it because we learn to measure the universe by effects, not by appearances. So here's what we know now. Our Milky Way is part of a local group of over 50 galaxies. Andromeda is 2.5 million light-years away, near enough to be our neighbor, far enough to break intuition. Beyond groups are clusters, stretching tens of millions of light-years, held together by gravity and dominated by dark matter. But then, this created a deeper mystery. If galaxies gather into groups, and groups gather into clusters, do clusters gather into something even larger? Because when astronomers began surveying the sky in bulk, thousands of galaxies at once, they didn't find randomness. They found something that looks like a skeleton, a vast pattern of filaments and voids, like luminous dust trapped on invisible threads. And that's where the story cracks open, because the universe is not just made of galaxies, it is made of the connections between them. We have this instinct that the universe is scattered, a black ocean with islands of light, stars, galaxies, a few bright dots. But that picture is wrong, because the universe is not sprinkled, it's wired, not with metal or electricity, but with gravity and time and invisible scaffolding. And once we see it, really see it, our idea of where we are starts to collapse, because the largest structure in existence isn't a single object. It's a pattern so enormous, so quiet, and so ancient that it makes the word distance feel childish. And here's the disturbing part. Even when we finally map that pattern, we still can't tell where it begins, because it doesn't. When we look up, we're tempted to imagine a center, a place where everything started, a cosmic downtown. Our brains love centers. Cities have them, storms have them, fires have them. But the universe does not give us that comfort. On the largest scales, the guiding idea in cosmology is that the universe is the same in all directions and, when averaged over truly vast distances, similar in every location. That's the cosmological principle. So the cosmic web has no hub, no throne, just structure, repeating structure, like a coastline that keeps fracturing into smaller coastlines the closer you look. And yet, if the universe is the same on large scales, why does it look so clumpy? Why does it look like it's tearing itself into threads? NASA describes it plainly. Galaxies, clusters, superclusters, and enormous walls are arranged in twisting thread-like structures, the cosmic web, with great empty regions in between. So instead of galaxies floating randomly, they gather along filaments. Those filaments intersect into knots, clusters stitch into walls, and between the walls there are voids, vast regions with far fewer galaxies than average. Voids aren't little gaps. Typical voids can span roughly 10 to 100 megaparsecs, about 30 to 300 million light-years across. That number sounds clean, but our intuition can't hold it. So let's translate it into something we can feel. Imagine this. You're flying over a massive city at night, but the power is out almost everywhere. Only certain streets still have lights. Only certain intersections still glow. From above, you wouldn't see a smooth, even blanket of brightness. You'd see lines, you'd see knots, you'd see dark neighborhoods where almost nothing shines. That's the cosmic web. Not because the universe prefers lines, but because gravity doesn't pull evenly. Gravity exaggerates differences. A little more matter in one place becomes a little more gravity. That gravity pulls in more matter. And over billions of years, small unevenness becomes a monstrous architecture. Here is the problem. If the early universe began hot and dense, why didn't it expand into perfect uniformity? Because it wasn't perfectly smooth to begin with. Even tiny variations, too small for human language to respect, were enough. Gravity is patient. Gravity doesn't need a dramatic shove. It only needs a slight advantage. And time. And the web forms like this. Matter flows into dense regions, leaving emptier regions behind, creating bubbles of emptiness surrounded by the brighter scaffolding. So the web is not decoration. It is the fossil record of how the universe grew up. But then comes the next unsettling detail. Even the empty parts of the universe aren't truly empty. NASA points out something that should make our skin go cold. The intergalactic medium, the material between galaxies, can be as thin as about 1 atom per cubic meter. 1 atom in a space you could step into. A small room's worth of nothing, holding almost nothing at all. That's not emptiness the way we mean it on Earth. That's cosmic thinness. Matter stretched almost to the edge of existence. And yet, even that faint haze matters, because it's part of the same structure, part of the same web. And that's why mapping the web is so hard. Most of it doesn't glow, which means we had to invent a way to see structure without seeing it directly. For most of human history, the sky was a dome, a flat ceiling of lights. Then astronomers began measuring redshifts, the way light changes when galaxies move away, so we could estimate distance and build a three-dimensional map. The Harvard-Smithsonian Center for Astrophysics describes how the second CFA redshift survey was run across about a decade, building a catalogue that helped reveal large-scale structure in galaxy distributions. And once you plot enough galaxies in 3D, something appears, not a smooth fog, but slices, like geological layers, showing clumps and emptiness, walls and gaps. Later surveys scaled this up into something far more terrifying. The Sloan Digital Sky survey didn't just add more points, it made the pattern undeniable, explicitly mapping clusters, voids, and the structural elements of large-scale galaxy distribution. This wasn't a poetic metaphor anymore, it was a measured geometry, a structure we could count. But this is where everything changes. Once we can map the web, we can also measure just how enormous its features are. NASA describes galactic walls as some of the largest known superstructures, stretching hundreds of millions of light-years across while remaining relatively thin. They even name specific examples. The Coma Wall, about 500 million light-years long. The Sloan Great Wall, about 1.4 billion light-years across. 1.4 billion light-years. That means if a beam of light left one end of that structure when the earliest complex life on Earth was only beginning its long struggle, that light still wouldn't be done crossing the wall today. And yet, even walls like this are not the universe. They're just threads in one region of the web, which raises the deeper question. If the universe has these gigantic features, why do we still say it has no center? When we say no center, we're not saying random. We're saying the pattern doesn't point to a privileged location. The web can look clumpy, filaments and voids, while still obeying the deeper idea that, on the grandest scales, the universe doesn't give one region a special status. It's like standing inside a forest. No matter where you stand, you can find dense patches and open clearings, but you can't find the center of the forest just by looking at the trees around you. And this is where the story cracks open. Because if the web is real, we should be able to watch modern science tracing it in finer and finer detail. And we are. NASA describes Hubble's role in observing the cosmic web through gravitational lensing, mapping matter by watching how gravity bends light. And now, newer projects are going even further. In March 2025, ESA's Euclid mission released early data including images and catalogues spanning tens of millions of galaxies. An early step toward a massive atlas meant to map large-scale structure in the cosmic web. This is what our era is becoming: cosmic cartography. Not just pretty pictures, but a measured skeleton of where matter actually sits. But then, there's a limitation that never goes away. The web we map is not the whole universe. It's only the web that light has had time to show us. Every galaxy survey has edges, not because the universe ends, but because our instruments do. Some galaxies are too faint. Some regions are hidden behind dust in our own Milky Way. Some distances are so extreme that our samples become thin, biased, incomplete. And even in the best surveys, statistics collide with a cruel truth. We only have one universe to observe from one location. That means some uncertainties can't be crushed just by wanting better data. They're baked into the fact that we're measuring the universe from inside it, through a limited window. So yes, the cosmic web is real. Yes, we can map it. But the map always comes with a warning label. This is the structure we can observe, and that distinction matters because it changes what knowing means. If you could drift out beyond our galaxy, far enough that the Milky Way becomes a single pale ember, and you looked back at the universe as a whole, you still wouldn't see the web with your eyes. Not directly. Most of it is too faint, too thin, too cold, too honest. We don't see the cosmic web the way we see the moon. We infer it from motions, from redshifts, from gravity's fingerprints, which means our next question becomes unavoidable. If light is all we have, how do we turn light into distance with precision? Because the cosmic web is not just a structure, it's a message written in photons that have traveled for millions and billions of years. And to read that message, we need a tool more powerful than intuition. We need to measure the universe with light itself, and that's where our next step begins. The universe never hands us a measuring tape. It gives us silence, it gives us darkness, it gives us light that's already old when it arrives. And that's the terrifying beauty of it. Because every time we point a telescope into space, we're not just looking far away. We're looking back through time, back through history, back through eras when Earth was unrecognizable. So the real question isn't, how far is that galaxy? The real question is worse. How do we know we're not lying to ourselves about the distance? Because space is too big for intuition, too big for guesses, too big for anything except measurement. And measurement, out there, has only one messenger: light. Out in space, we can't touch anything. We can't walk to the nearest star. We can't place a marker on a distant galaxy and stretch a tape between us. So astronomy does something almost unsettling. It turns light into a ruler. NASA puts it in plain language. A light year is the distance. Light travels in a year about 5.88 trillion miles, or 9.46 trillion kilometers. That's not a poetic unit. It's an admission. It's us saying, we can't measure this the way our bodies measure, so we will measure with the fastest thing that exists. Because in the cosmic wilderness, light isn't just illumination. Light is evidence. Evidence of distance, evidence of motion, evidence of time. And that's where the story cracks open. Because once we treat light as evidence, we realize something quietly brutal. Every photon we catch is already a message from the past. When we look at the moon, we see it as it was a little over a second ago. That feels trivial. But as we climb the scale ladder, a little over a second ago turns into something monstrous. Minutes, hours, years, millions of years. We don't have to imagine time travel, we're already doing it. Every night. Because light doesn't teleport, it travels. NASA describes it as racing through space at about 186,000 miles per second, or 300,000 kilometers per second. So when we say a galaxy is 2 million light years away, we're also saying something that should feel heavy. The light left that galaxy 2 million years ago, before modern humans existed, before our languages formed, before our cities became ideas. So distance isn't just space. Distance is history. But then, the universe introduces a new problem. Sometimes light doesn't just arrive old. Sometimes it arrives changed. Here's the strange part. When astronomers spread galaxy light into its spectrum, breaking it into its colors, they found patterns shifting, not random, not subtle, systematic. NASA explains cosmological redshift like this. As space expands and galaxies move farther apart, their light stretches, elongating into longer wavelengths, shifting toward red. ESA describes the same core idea. The wavelength is stretched so the light appears shifted toward the red part of the spectrum. So redshift isn't just a color thing, it's a physical signature that space itself is expanding. And now we have two pieces of the puzzle: distance, carried by light's travel time; expansion, written into light's stretched wavelength. But that creates a bigger problem, because redshift tells us that distant galaxies are caught in expansion. It tells us something is moving away. It does not automatically tell us how far away it is. To get distance, we need a second tool, something with a known brightness, something the universe provides, like a lighthouse. This is where astronomy becomes almost forensic. If we know how bright something truly is, and we compare it to how bright it appears from Earth, we can estimate distance, not by guessing, by comparison. Astronomers call these objects standard candles. Two of the most important standard candles ever discovered are Cepheid variable stars, type Ia, supernovae. They are the backbone of the cosmic distance ladder, and the ladder exists for one simple reason: no single method reaches all distances. Cepheids are stars that pulse, brighten and dim on a regular schedule, and Henrietta Swan Leavitt discovered something that changed everything. The period of the pulsation is linked to the star's true brightness. NASA's Star Child explains the idea. Once you measure a Cepheid's period, Leavitt's relationship tells you its brightness, and by comparing that to how bright it looks from Earth, you can extract distance. This is an astonishing concept. A star that beats like a heart becomes a ruler, and Cepheids are bright enough to be seen in nearby galaxies, which is why they became a bridge from our galaxy to other galaxies. This is how Edwin Hubble helped establish that some nebulae were actually galaxies far beyond the Milky Way, by using Cepheids as distance markers. And once Cepheids worked, the universe expanded overnight. But then the ladder hits a limit. Cepheids are powerful, but not powerful enough to reach deep into the universe. So astronomy needed a brighter flame, a standard candle so violent it could be seen across unimaginable distance. Type Ia supernovae are exploding stars so luminous they can outshine entire galaxies for a short time. NASA explains that missions like the Nancy Grace Roman Space Telescope will use Type Ia supernovae to measure cosmic distances and track how the universe expanded over time. And NASA's Hubble Science pages describe why they matter. Type Ia supernovae are brilliant enough to be seen much farther than Cepheids, allowing measurements out to distances where expansion becomes clear. This is the terrifying elegance of the method. Cepheids help measure distances to galaxies close enough to resolve individual stars. Supernovae extend that reach far beyond, because they are bright enough to be seen from much farther away. But this creates another question. If Cepheids and supernovae are both distance tools, why do we need a ladder at all? Why not just pick the best one and measure everything? Because the universe doesn't let us. We can only calibrate some distance tools up close, and some tools only appear far away. That mismatch forces overlap. A ladder. NASA describes this climb directly, how Cepheids and Type Ia supernovae are combined to step outward into the distances where expansion can be measured. The logic is simple, but the consequences are enormous. First, we use geometric methods for nearby stars, like parallax, the apparent shift as Earth moves around the Sun, that anchors Cepheids, so we trust their true brightness. Then Cepheids anchor supernovae, so we trust their true brightness. Then supernovae carry our measurements outward into the deep universe. It's not one measurement, it's a chain. And in a chain, the fear is obvious. A small error early becomes a catastrophic error later. So, astronomers obsess over a single word: uncertainty. Astronomy is not just finding numbers, it's proving those numbers are stable. Because when we claim a distance to a galaxy, we're not claiming perfection. We're claiming something like, we measured this, we cross-checked it, and here's how confident we are. This is why astronomers don't rely on one telescope, one data set, or one method. They cross-verify. They look for systematic errors, biases that don't average out. They ask questions like, did dust dim the light? Did crowded stars contaminate the measurement? Did our instrument drift? Did we assume the wrong intrinsic brightness? And this is where modern astronomy becomes almost ruthless. It tries to destroy its own measurements before the universe does. Over decades, our distance measurements sharpened because our tools sharpened. ESA's Gaia mission produced a star catalogue with parallax measurements for over 1.3 billion stars, allowing direct distance estimates for a significant set of them. That matters because parallax is one of the cleanest anchors we have. Geometry, not astrophysical assumptions. Better anchors make the ladder stronger. NASA describes how Webb and Hubble together tested a critical question. Were Hubble's Cepheid measurements biased by crowding nearby stars contaminating the signal? The combined conclusion, as described in NASA's report on the expansion rate puzzle, the Hubble measurements remain reliable as astronomers climb farther along the cosmic distance ladder. That's not just a technical detail, that's the entire ladder being checked for cracks. NASA's Hubble materials also summarize the importance of Cepheids in the key project legacy and later work, including measurements of the Hubble constant and continued scrutiny of uncertainties. The theme is consistent. Astronomy didn't solve distance once, it kept refining it, because every decade brings sharper instruments and new ways to test old assumptions, and as the precision improves, something else happens. Our measurements begin to disagree in ways that are not comfortable, but that's a story for later. For now, we stay with the foundation: light. Picture this. We're standing in a long hallway. At the far end, someone holds a flashlight and slowly walks away from us. The light still reaches us, but it starts to feel weaker, more distant. Now imagine the hallway itself is stretching, silently lengthening while the person walks. The light isn't just traveling through space. Space is changing beneath it. That stretching is what redshift is telling us. The light's wavelength is stretched as the universe expands. And once we understand that, we understand the next step. To measure the universe, we don't just measure how bright something looks. We measure how its light has been altered by time and expansion. And when you look at a distant galaxy, really look, you're not seeing a place. You're seeing a message that survived a journey across cosmic history, a message that space stretched, a message that arrives older than our species. And the only reason we can place that galaxy on a map is because we learned to treat light like evidence and to build a ladder strong enough to climb beyond instinct. So now we have the toolkit: light as time travel, redshift as the signature of expanding space, Cepheids as the first true rung beyond our neighborhood, Type Ia supernovae extending the ladder into the deep universe, cross-checks from missions like Gaia, Hubble, and Webb strengthening the foundation. But then comes the most haunting question of all. Even with all this, even with the best distance ladder we've ever built, what is the farthest boundary light can possibly show us? Because there is a horizon in the universe that no telescope can cross. Not because we lack technology, but because the universe itself has rules about what can reach us. And that's where we go next. Into the observable universe, the farthest we can see. We like to believe the universe has edges, a border, a wall, a last page. But the most disturbing part is this. The farthest thing we can see is not the farthest place the universe has reached. There is a boundary out there that looks like the end of everything. And yet, it isn't an edge in space. It's an edge in information. It's the limit of what light has had time to bring us. And if we misunderstand that, then we misunderstand our entire place in the cosmos. Because out there, in the black, the universe has arranged a cruel trick. It lets us see almost all the way back to the beginning, but it refuses to let us see beyond a certain line, and that line is not where our intuition says it should be. When astronomers say the observable universe, they're not talking about what our telescopes are powerful enough to detect. They're talking about something colder, a physical limit, a limit built into reality itself. Light moves fast, about 186,000 miles per second, or 300,000 kilometers per second. But it is not infinite, and the universe has an age, about 13.8 billion years. So it feels like the answer should be obvious. If light has been traveling for 13.8 billion years, then the observable universe should be 13.8 billion light years in radius. But that answer is wrong, and that's where the story cracks open. Astronomers calculate that the observable universe today has a radius of about 46 billion light years, not 13.8, 46. That number is not poetic, it's violent. It shatters the simple picture we carry in our minds, and it raises an uncomfortable question. How can we see a boundary 46 billion light-years away in a universe that's only existed for 13.8 billion years? This should be impossible, and yet it's real. So we need to say this clearly. The observable universe is not defined by how far light travelled. It's defined by how far away the source is now. And now has been changing the whole time, because space itself has been stretching. Picture this. You're walking down a long hallway toward a door. You take a step, and you get closer. But then the hallway subtly stretches, not enough for you to notice in a single moment, but enough that the door is always drifting away while you walk. So after a while, you realize something terrifying. You did walk the whole way. You did cover the distance, but the distance didn't stay the same while you were moving. That's what the universe does to light. Light travels for billions of years, but the fabric of space keeps expanding while it travels. So the starting point of that light ends up farther away today than it was when the light began its journey. This is where people get trapped. We imagine galaxies flying outward like shrapnel, but on the largest scales, it's not galaxies breaking a speed limit by moving through space. It's space itself expanding. NASA has said this plainly. The apparent faster-than-light recession of distant galaxies does not violate Einstein's special relativity, because it's the expansion of space doing the separating. Einstein's limit, nothing outruns light locally, still holds. But the universe has found a loophole that feels almost unsettling. Space can grow, and growing space can carry distant galaxies away so quickly that the distance between us and them increases faster than light could cross it. Not because anything is cheating, but because our intuition was never built for an expanding reality. So what exactly is at that boundary? What is the farthest thing we can see? It isn't a galaxy. It isn't a star. It's something stranger. A glow. A faint, ancient afterimage filling the entire sky. The cosmic microwave background. The oldest light we can observe. NASA describes this afterglow as light that was emitted roughly 375,000 years after the early universe's inflation era, travelling across the universe largely unimpeded ever since. That number matters, because before that moment, the universe was not transparent. It was a hot, dense plasma, like a blinding fog of charged particles. Light couldn't travel freely, it kept colliding, it kept getting scattered. So the cosmic microwave background is not just far, it is a boundary in time, a final curtain, the moment the universe became clear enough for light to survive the trip. That's why the observable universe has an edge, not because reality ends, but because visibility ends. There are two walls we hit at once. First, time. Light from beyond a certain distance simply hasn't had enough time to reach us since the beginning. That's the basic limit created by the speed of light and the age of the universe. Second, opacity. Even if the universe extended beyond what the cosmic microwave background shows us, the earlier universe was so dense and hot that light couldn't carry information in a straight line. So we are locked inside a view. A cosmic sphere of information centered on us, not because we're special, but because light has rules, and every observer anywhere would have their own observable universe centered on them. That's the quiet, unsettling truth. The observable universe is not a privileged place. It's just what causality allows. So what about everything beyond? We need to speak carefully here. Science does not pretend to see what it cannot measure. We can say this with confidence. The observable universe is the region we can receive signals from, light, or any information traveling at or below light speed, given the universe's age and expansion. The universe beyond that may exist, but it is not directly observable to us right now, because no signal from there has reached us. So, observable is not small, it is already monstrous, a radius of about 46 billion light-years, a diameter of about 93 billion light-years, and yet it may still be only a fragment of the whole, not a guess, not a fantasy, just an honest boundary drawn around what evidence can touch. And here's the strange part. The observable universe is not a fixed object. It changes as time passes. As the universe expands, distances change. As light continues to arrive, our observable horizon can grow. But expansion also creates a deeper complication, one that astronomers wrestle with constantly. NASA describes how the universe's expansion history is not simple. It slowed under gravity early on, then began accelerating billions of years later, linked to what scientists call dark energy. So the universe isn't just large, it's dynamic. Its scale is a living thing. And that means distance is not just a measurement. It's a story about time, expansion, and what light has managed to survive. And now, for a second, place yourself inside it. You are standing on a thin crust of rock, on a planet that feels enormous when you're down here. But above you is a sphere of ancient light, 46 billion light-years in every direction, pressing in silently. Every point on that sphere is the farthest message you can ever receive from that direction, given the universe's history so far. That is not just scale, that is limits. And limits are not depressing, they're clarifying. They tell us exactly what kind of universe we live inside. So we've found the edge of what we can see, a horizon made of time, a boundary written in light. But this is where everything changes, because the universe doesn't only expand, it expands in a way that can change what distance even means. And if space itself is stretching, then the most terrifying possibility isn't that the universe has an edge. It's that the universe can create regions that will never be reachable by light, no matter how long we wait. Not because they're hidden, but because expansion keeps pulling them away. And that raises the next question. If expansion can reshape the observable universe, then what does distance even mean in a universe that won't stop growing? We think distance is a simple thing, a line, a number, a gap between two places. But in the universe, distance is unstable. It stretches, it drifts, it changes while we're looking at it. And that single fact fractures almost every common sense image we carry in our heads. Because the universe is not just big, it is growing. So when we ask, how far away is that galaxy? We're asking a question with a trap inside it. Far away. When? Now? When the light left? Or when the universe was young enough to still feel small? Here's the disturbing truth. The universe can be older than 13 billion years and still place the edge of what we can see at about 46 billion light-years away. That should feel impossible. And yet it's the key to everything. The universe is about 13.8 billion years old. Light has a speed limit. Nothing carrying information outruns it in the local sense. So our instincts say the visible universe should have a radius of 13.8 billion light-years, but the observable universe has a radius of about 46 billion light-years. The reason is almost cruelly simple. Space itself expanded while the light was traveling. So the light did not travel 46 billion light-years. The light traveled for 13.8 billion years. But the place it came from is now much farther away, because the fabric between us stretched over time. Distance, in cosmology, is not a frozen ruler. It's a moving target. And this is where the story cracks open. Once we accept that, we have to accept a second consequence. The farther we look, the faster the universe seems to run away. Edwin Hubble's observations, building on the mathematics of Georges Lemaitre and Alexander Friedman, revealed a pattern. On average, galaxies are receding, and the farther away they are, the faster they recede. That relationship is known as the Hubble-Lemaitre law, This is not just trivia. This law is the universe admitting it has a rhythm, a scaling rule, a rule that tells us the expansion is not something happening over there. It is happening everywhere. So when we say a far galaxy is receding faster than a near one, it can sound like a violation, like cosmic objects are breaking the speed of light. But that's where people get trapped, because what's moving isn't always the galaxy. It's the space between us and the galaxy expanding. Einstein's special relativity is still intact. Locally, nothing outruns light. NASA explains this clearly in the context of cosmology. Galaxies can appear to recede faster than light without violating relativity because it's space expanding, not objects locally traveling through space at forbidden speeds. This distinction matters because moving through space is one kind of motion, but space itself stretching is another, and the universe chose the second one, which creates a deeper, more unsettling realization. If space can stretch, it can stretch forever, and the meaning of distance becomes something almost philosophical. Picture this. We draw two dots on a rubber sheet. Those dots are galaxies. Now we stretch the sheet. The dots don't need to crawl across the rubber. They don't need engines. They don't need to travel. And yet, the distance between them grows. That's the cosmic expansion idea in its simplest form. And NASA describes the observational signature of that expansion directly. Light from galaxies stretches to longer, redder wavelengths as it travels through an ever-expanding universe. So even the light carries evidence that the space it crossed did not stay still. But then comes the next twist. The expansion of the universe hasn't been the same forever. It has a history, and that history changes the fate of everything we will ever see. In the earliest moments after the Big Bang, the universe expanded extremely rapidly. After that, gravity, matter pulling on matter, worked to slow the expansion down. But the cosmos didn't stay in that phase. NASA states it plainly. 9 billion years after the universe began, the expansion started to speed up, driven by what scientists call dark energy. That means for billions of years, expansion was slowing. Then something changed, and the universe began accelerating. This is not a poetic metaphor. It is a measured fact supported by multiple lines of evidence, including observations of distant supernovae, explosions that served as distance markers and revealed the accelerating expansion. So expansion isn't one simple motion. It's a story with phases. And once acceleration enters the story, distance becomes even more dangerous, because acceleration creates horizons, not just how far we can see, but how far we can ever be connected to. When we say the universe expands, we are not picturing a fireball expanding into a larger empty room. There is no outside room. Expansion is not the universe filling empty space. Expansion is space itself changing scale. This is why redshift exists, why wavelengths stretch as they cross the universe. And this is why the observable universe can be so much larger than the universe's age might naively suggest. Distance is not just how far light traveled. Distance is how far away that place is now after space expanded during the journey. That alone is enough to break our intuition, but acceleration adds something even colder. Some regions of the universe are being carried away so quickly that no future signal from them can ever reach us. This is where the universe becomes truly unsettling. We tend to think, if we wait long enough, light will arrive. But accelerated expansion can create a permanent separation, a cosmic event horizon, regions from which light emitted in the future will never reach us. Not because light is weak, not because our telescopes are small, but because the space between us grows too fast. The observable universe is already defined by what can reach us given the universe's age and expansion. Acceleration implies something harsher. There are places that exist, real places with real galaxies, that are not just unseen now, but forever unreachable in principle if the expansion continues in an accelerating way. This is why distance in cosmology isn't just geometry, it's destiny. We can say receding faster than light, and our brains revolt. So let's translate the feeling without breaking the science. Light travels about 186,000 miles per second, or 300,000 kilometers per second. At that speed, you could circle Earth more than 7 times in a single second. And yet, on the largest scales, space can widen so relentlessly that even light cannot close the gap. Not because light slows down, but because the finish line keeps moving away. That is the kind of universe expansion describes, and it leads to a final quiet truth. The universe's scale is not a single number. It is a living quantity. When people ask, how big is the universe? They often want one clean answer, but the universe refuses, because big depends on the definition. The age of the universe is about 13.8 billion years. The observable radius today is about 46 billion light years, because space expanded during the time light travelled. Expansion has a history. It slowed, then later accelerated, tied to what we call dark energy. And the expansion rate itself is a frontier of modern measurement, with ongoing debate and increasingly precise observations. So distance is not just where something is. Distance is how the universe has behaved between us and it. And this is why cosmology feels like a cosmic mystery. The deeper we measure, the more the meaning of our words changes. If you stare at a distant galaxy long enough, it stops feeling like a place. It starts feeling like a message that barely survived, a message stretched by expansion, a message carried across a universe that changed its own scale mid-journey. And the unsettling part is this: even if we built perfect ships, even if we waited forever, some parts of the universe would still remain out of reach, not by choice, but by geometry and time. So now we understand the trap. Distance is not fixed. Scale is not static. The universe is not a photograph. It's a film, still playing. And that creates the next question. If every layer of scale changes what the next layer means, how do we put the whole ladder together, human to Earth to solar system to galaxy to cosmic horizon, without losing the truth in the transitions? Because the hardest part isn't learning one number. The hardest part is building a single mental structure that can hold all of them at once. And that's where we go next. We've all seen the same image: a neat row of planets, a glowing spiral galaxy, a universe that looks almost understandable. But that picture is a lie. Not because anyone is trying to deceive us, but because no single image can hold true scale. If we draw the solar system so the planets are visible, the distances vanish. If we draw the distances honestly, the planets become dust. And if we try to show the universe, the page collapses under the weight of the numbers. That's the uncomfortable truth. The universe is not hard to understand because it's complicated. It's hard because our intuition fractures under scale. And yet, we still learn to measure it, not by imagining, but by building a ladder. One rung at a time, we started where our bodies live: meters, rooms, streets. Then we stepped outward, carefully into kilometers, and continents, and an Earth we finally learned to see as a sphere. We placed the moon at its real distance. We stretched the solar system into its true dry emptiness. We crossed the interstellar gap where even light years begin to feel small. Then we entered the Milky Way, a structure nearly 100,000 light years across, a disk of stars, not a dot. And we learned a disturbing detail. Even our galaxy, this colossal city of light, holds only one address in a crowded neighborhood. The universe is not a collection of isolated islands, it's a map of islands. And then, something even stranger. A cosmic web, a structure so vast it can't be seen in a single glance, only inferred. So now we arrive at the question that ties everything together. How do we connect every rung without breaking the truth of scale? Here's the problem. Our brains want one picture that explains everything, one diagram that makes the universe feel graspable. But scale doesn't work that way, because scale is not linear to human feeling. 1,000 feels big, 1,000,000 feels like another big number, 1,000,000,000 feels like a word we say without meaning it. This is why space misconceptions survive so easily, because the visual shortcuts that make space look right almost always make it wrong. A planet drawn larger so you can see its rings quietly destroys the emptiness that defines the solar system. A galaxy drawn as a glowing swirl beside another galaxy hides the abyss between them, and the most brutal deception of all, when the universe is drawn as a bubble with a center. Because the universe doesn't give us a privileged viewpoint, it gives us a limit, a horizon, a boundary made of light and time. And that boundary is not small. The observable universe stretches about 46 billion light years in every direction. That number isn't just large, it's psychologically radioactive. It dissolves intuition. So we don't rely on intuition, we rely on measurement. We hold it the same way we hold deep time, with a system, with steps that connect, with a scale ladder. Rung 1, Earth and the baseline. If our baseline is wrong, everything above it collapses. So we anchor in what we can measure directly. Earth's size, its curvature, its diameter, its orbit. Then we reach outward to the first great yardstick. Rung 2, the astronomical unit. The distance from Earth to the Sun is about 93 million miles, or 150 million kilometers. That's one astronomical unit. It's the first unit that makes the solar system readable, not because it makes it small, but because it makes it consistent. Rung 3, the light year. Then we hit the first truly violent unit. A light year is not time, it's distance. It's how far light travels in 1 year, about 5.88 trillion miles, or 9.46 trillion kilometers. And this is where our normal sense of far breaks, because now distance becomes time travel in reverse. When we look out, we look back. Imagine this. You're standing at night in a completely dark field, and someone hands you a single flashlight. That beam is all you get. It's the only information you can send or receive. Now imagine every star, every galaxy, every structure in the universe is only visible where the beam reaches, and where the light has had time to return. That's our situation. We do not see space. We see light that survived the journey, and the deeper we look, the older the light becomes. This is why the universe is measurable, but not fully visible. And this is where the story cracks open. Scientists don't claim certainty because it sounds impressive. They claim it because the measurements agree, even when made in different ways. Within the solar system, we can measure distance using radar, timing how long signals take to bounce back. That's not philosophy. That's a stopwatch. For nearby stars, astronomers use parallax, a tiny shift in apparent position as Earth moves around the Sun. And today, missions like ESA's Gaia have measured distances for well over 1 billion stars, turning our part of the galaxy into a geometric map instead of a guess. From our position inside it, counting stars is hard, but combining surveys and models, NASA describes the Milky Way as a disk about 100,000 light-years wide, made of approximately 100 billion stars. And now translate that into human effort. If we tried to count 1 star per second without sleeping, it would take thousands of years just to reach 100 billion. That is what our galaxy actually means. A city so large that human labor becomes meaningless inside it. NASA describes the universe as about 13.8 billion years old, based on multiple measurements tied to expansion and the oldest stars. And missions studying the early universe, like Planck, reinforced that same scale. That's not a single fragile estimate, it's a convergence. There is a wall we cannot see through, not because it's made of stone, because before a certain moment, the universe was opaque, too hot, too dense, too ionized for light to travel freely. Only after roughly 380,000 years did space become transparent enough for light to move across it. That ancient light still fills the universe today. The cosmic microwave background, a boundary not drawn by imagination, but by physics. And here's the strange part. Wherever you are in the universe, the observable universe has a center, because the horizon is built around the observer. Not because you matter more than anyone else, but because light has only had so much time to reach you. So the question isn't, where is the center of everything? The question is darker. How much of reality will we never be able to see, no matter how long we wait? This is where honesty matters. Science doesn't end with "we don't know." It ends with "we know exactly what we don't know." We observe gravity behaving as if there is more mass than we can see. We observe expansion behaving as if something is pushing space apart. Planck results described a universe where dark matter and dark energy dominate the budget, while their true nature remains mysterious. That is not speculation. That is a measured imbalance. The observable universe is not everything. It's the portion we can, in principle, receive light from. Britannica describes the observable universe as having an edge in this sense, about 46 billion light-years away in any direction. But that is not the edge of the universe. It's the edge of our access, and the difference matters, because it means there may be more structure, more galaxies, more history, not as fantasy, as a consequence of finite light speed and finite time. We can measure the ladder, we can measure the rungs, but we also admit the horizon. And that balance, precision without arrogance, is one of the most human things we've ever done. So now we can finally hold the full shape of the journey, from human scale to Earth to the solar system, to a Milky Way 100,000 light-years wide, to an observable universe stretching 46 billion light-years in every direction. No image can show it, but our measurements can connect it, and that creates a deeper mystery. Because if we can locate everything, if we can build the ladder, if we can map the cosmic web and read the afterglow of the Big Bang, then one question remains, sharper than all the rest. Where are we, really, inside this scale? Not in a poetic sense, in a precise sense. A calm, well-defined answer. And that's where we go next. We spend our whole lives learning where we are, a room, a street, a city, a country, and it feels complete. But then we look up, and that certainty fractures, because the universe doesn't just contain us, it swallows the idea of us. And here is the disturbing truth. We can name our location in the cosmos with calm precision, but the scale behind that location is so large, it collapses human intuition. We are not lost. We are measurably placed inside something almost unimaginably vast. But then, the moment we understand where we are, a deeper question appears. If we can locate ourselves this clearly, what does it mean that the universe is still far larger than anything we can ever see? Let's say it plainly. We are on Earth. Earth is orbiting the Sun. The Sun is one star among hundreds of billions in a galaxy called the Milky Way. And the Milky Way is one galaxy in a small family called the local group. This isn't a metaphor, this is the result of a long chain of measurements built by human minds that refuse to accept it's too big. We didn't guess our cosmic address. Astronomers measured it using light, motion, gravity, and time, over decades, across generations, with instruments built by NASA, ESA, and teams around the world. And that's why our position is not special. It's simply, well-defined. Here's the strange part. Every direction we look, the sky seems to wrap around us like a dome. It's easy to feel like we're at the center, but the universe doesn't have a center in the way our minds want a center. Not like a city with a downtown, not like a globe with a marked point. The center is a trap built by human instincts, because center is what our brains use to survive. We evolved to navigate forests and rivers, to judge distances across fields, to track threats within a few seconds of movement. We did not evolve to feel what it means for the universe to be 13.8 billion years old. We did not evolve to accept that the oldest light we can observe, the cosmic microwave background, was released when the universe was only about 375,000 years old. And we did not evolve to understand that the observable universe today reaches a current radius of about 46 billion light years in every direction. That single fact should feel impossible, because it means the edge of what we can see is not 13.8 billion light years away. Space has been stretching the whole time. The universe has been expanding while the light was traveling. So the cosmic horizon is farther than our instincts would allow, and it creates an unsettling realization. We can locate ourselves, but we cannot locate the full universe. Not because we lack intelligence, but because physics itself places a boundary on what information can reach us. When we say the observable universe, we are not talking about the entire universe. We are talking about the region of space from which light has had enough time to reach us since the Big Bang, and could reach us given the way space expands. It's a bubble, not an edge to reality, just an edge to what we can receive. And the boundary of that bubble is written into the oldest light we can detect, the cosmic microwave background, what NASA calls the oldest light we can observe. That glow is not a wall, it is a timestamp. It's the universe's childhood, still arriving. And beyond it, there is more universe. But no light from beyond that boundary has reached us yet, and some of it never will. Now we return to the simplest part, where we are, not in philosophy, in structure. We are in the Milky Way galaxy, and the Milky Way is roughly 100,000 light years across. We are not near the center. Our solar system sits tens of thousands of light years from the galactic center, often described around 25,000 to 27,000 light years away. That is our neighborhood inside the galaxy. Then the Milky Way is part of the local group, a small gravitational family of galaxies. And our nearest massive neighbor is Andromeda, about 2.5 million light years away. 2.5 million. That number is cold until we translate it into something human. If Earth were the size of a grain of sand, Andromeda would not be across the street, it would be across a continent. And even then, the analogy fails, because our minds still want to shrink it. So we use what we've used all along, light. Light doesn't care what we can imagine. Light only cares what is real. Tonight, if you step outside and you look up, you are not seeing space, you are seeing history. Some of that light left its star before our species had language. Some of it left before agriculture. Some of it left before the first cities ever breathed. And the cosmic microwave background, that faint afterglow, left when the universe itself was only a few 100,000 years old. Not millions, not billions, a few 100,000. When the first atoms formed and space finally became transparent enough for light to travel freely. This is why the universe is not just big, it is layered in time. Every distance is also a look backward, and that is why our understanding of scale is not a luxury. It is the only way we know what is true. Imagine this. You're standing on a beach at night. The ocean is calm, the air is cold, and a heavy fog sits on the water. You can see the waves close to your feet. You can see the water out to the fog line. And then it disappears. Not because the ocean ends, but because your sight ends. That fog line is the observable universe, The ocean is the universe itself. We are not claiming the water stops. We are admitting we can only see so far. And what makes this truly disturbing is that the fog line isn't just about distance. It's about time. It's about expansion. It's about what information is physically allowed to reach us. There are things we can state calmly. The universe is about 13.8 billion years old, based on measurements including Planck and other cosmological observations. The cosmic microwave background is the oldest light we can observe, released when the universe was only about 375,000 years old. And the observable universe today has a current radius of roughly 46 billion light-years, because space has been expanding while the light travelled. Those are not guesses, they are measurements, with uncertainty ranges, cross-checks, and a century of scientific argument behind them. But then, even after all of that, there is still a boundary we can't cross. Not with rockets, not with telescopes, not with hope. Because beyond the observable universe is not darkness, it's simply not yet seen, and some of it is never seen. So, where are we? We are on a small planet orbiting an ordinary star. That star is embedded in the disk of an ordinary spiral galaxy. We are not at the centre of that galaxy. We are not at the centre of the local group. We are not at the centre of the universe, because centre is not a meaningful concept on that scale. What we are is located. We can draw our cosmic address like a map. Earth, the Sun, the Milky Way, the local group, the observable universe. And beyond that, a reality we can't fully measure yet, but can define as more than observable. That's the line we end on. Not mystery for mystery's sake, but clarity. We are physically small, so small we can disappear under a hand, but we are cognitively vast. We can take photons that crossed billions of light years of expanding space and turn them into an understanding. We can look into the oldest light in existence and read the universe's childhood. And that is the quiet truth. The universe is not built for our intuition, but it is not hidden from our minds. We do not conquer the cosmos by reaching it. We do it by measuring it, by naming what is real, even when it dwarfs us. And in that contrast between our fragile bodies and our relentless understanding, we find something steady, not comfort, not certainty, but perspective. Because once we finally see where we are, we also see what we are, a species that can stand in the dark beneath an ocean of stars and still learn the shape of the unimaginable. We started this journey believing the universe was something we could picture, a diagram, a clean line of planets, a galaxy as a glowing spiral, a cosmos that fits inside the frame of a screen. But the true scale of the universe doesn't fit inside frames. It breaks them. It forces us to admit something uncomfortable. Our intuition was never built for this. Our eyes were designed for faces across a room, for firelight on skin, for the distance between a shelter and a river, not for light years, not for galaxies, not for horizons made of time. And yet, we didn't turn away. We built a ladder out of measurement. We climbed from what we can touch to what we can only infer, from Earth to the Moon, to the Sun, to the outer dark, from a single star system to the Milky Way, to the local group, to a universe threaded into a cosmic web. And somewhere along that climb, something changed. Because the true scale of the universe doesn't just teach us science, it teaches us what we are. It shows us that our physical size is not the measure of our significance. A human body is small, fragile, a few breaths away from silence, but our reach is not measured in muscle, our reach is measured in understanding. We can take a faint smear of light from the edge of the observable universe and turn it into a fact. We can stare into the afterglow of the early cosmos and recognize it as the universe's first light, still moving through space. That ability is not normal, it is rare, it's almost unsettling, because it means the universe produced something that can look back at it. The cosmos is vast, yes, but it is not meaningless, because meaning is not something the universe hands to us like a gift. Meaning is something we build, with language, with memory, with shared questions, with the stubborn refusal to accept ignorance as a final answer. And when we finally grasp the scale, truly grasp it, we feel two emotions collide inside us. The first is humility, not the shallow kind, not the kind that says, we are nothing. The deeper kind that says, we are not the center, we are not special in location, we are not the reason the universe exists. We are simply a point, a quiet address inside a structure so large it shatters imagination. But then the second emotion arrives, because even if we are not central, we are still capable, we are still here, we are still able to measure what dwarfs us. Think about that. A species that lived most of its history under fear of storms and darkness now builds instruments that can read the universe's expansion. A species that once painted animals on cave walls now maps the motion of galaxies. This is not a conquest. It's something stranger and more beautiful. It's a relationship. We are not separate from the universe. We are the universe in one of its rare moments, becoming aware of itself. Every atom in our bones was forged in stellar furnaces. Every breath is chemistry, borrowed from ancient cosmic processes. Every thought is a physical event inside matter that has been traveling since the beginning. So when we ask, how big is it? We're not just asking for numbers. We're asking what kind of reality could contain us? What kind of reality could produce minds that can measure their own horizon? And here is the quiet truth we end on. The universe is larger than our bodies, larger than our instincts, larger than any picture we will ever draw. But it is not larger than our ability to learn. And maybe that's the most human thing of all. We cannot hold the universe in our hands, but we can hold its scale in our minds. And when we do, our ordinary life, our streets, our rooms, our struggles, doesn't become smaller. It becomes more precious. Because in a cosmos this vast, every moment of understanding is rare, every shared breath is improbable, and every time we look up and choose to learn instead of turning away, we prove something quietly, profound, even here, on this small world under an ancient sky. We belong to something enormous, and we are awake inside it,